Namaskar my dear friends. So we have already covered STM32 microcontroller. The target device was STM32L053. There are various devices equivalent to this particular device, okay, and all of them can be used with as a fundamental of this particular session, okay. So what we'll do in this session is we'll try to understand quickly all the peripherals that we have seen earlier in one nutshell. So this will be like kind of a complete package for complete circuit design of STM32 microcontroller with all the peripherals together, okay. So let me summarize the topics that we will cover in this session quickly. First of all, we'll try to understand how we can design the microcontroller symbol. Then we'll design the power supply for this particular microcontroller device, how we can programming and debug, okay. There are different techniques of programming and debug, so we'll see SWD programming, that is serial wire debug programming. Then we'll try to understand how we can design the reset circuit or reset switch. Then we will also talk about boot mode, okay. Then we'll have various applications of how we can connect LEDs, push buttons, deep switches, and there are different applications as well in the circuit, right. Then we'll try to understand how we can connect our different voltage parameters to the ADCs so that we can measure the ADC values for the particular various parameters. Even sensors and all we will try to use. Then we can generate PWMs. We will also see the interface for temperature sensors, IR receivers, EEPROM that will be used for our live data storage. So EEPROM with I2C we'll try to understand. Also we'll try to see a buzzer that we can be used for our alarm application, okay. So we can use this buzzer for beep beep sounds based on the temperature variation, or maybe some alarm that is happening in our applications. There are various applications that is there in our industries, whether it is medical application or industrial application or automotive applications or even consumer appliances or home appliances. Wherever you see there may be a requirement of buzzers where you need to produce some alarm based on the different fault conditions or different a threshold value that it has reached. Then we will also see external interface with so that it can drive the other daughter board or something, some other connected board. We'll see some of the communication interface like RS232, RS485, RS422 also will be almost same as RS485, okay. Then we'll see the applications of multiplexer switch, USB to UART bridge, okay. So USB to UART bridge is very much useful in this kind of applications where you have to directly connect to your PC, that is your laptop or desktop, to the particular board that we have designed. Some more applications that we'll try to understand in this session is external ADC and its applications, how we can utilize external ADCs for measurement of different parameters in the board. Then we'll also use some external voltage reference for this external ADCs. We'll also see NTC temperature sensor, that is negative temperature coefficient sensor. Generally this will be very sturdy device which are used to measure the environment temperature. Then we'll see the application of ambient light sensor, which can be used in your home appliances or smart homes, where you have to measure the ambient light capabilities, and based on that you can switch on switch off lights. And we'll also see the pressure sensor application. So this is how in one summary I have I have summarized all the parameters that we are going to see in this particular session, okay. So let us start one by one this complete circuit design of microcontroller of STM32, okay. So STM32 device is one of the best popular device that is there from ST Microelectronics, and ST Microelectronics devices, as you can see, are very popular, as well as it is because the main reason for this particular device popularity is it is very easy to develop, okay, and very conveniently available, and the programming process and everything is also very easy. Like STM32 Cube IDE is available, STM32 Cube IDE, okay. So with this you can generate your code and you can program your device. All right, so let us try to understand the microcontrollers. So this is the microcontroller symbol that I have designed, and as you can see, I have categorized all the pins as port wise. So PA0 to PA15, then PB0 to PB15, and similar to that PC0 to PC15. Okay, another peripherals are also there, like PD2, then PH0, PH1, and boot pin is here, and then NRST, that is reset pin, is here. The all the power supply pins are here, like LCD supply, then VDDA, VDD USB. We have power supplies pin, VDD pins, and VSS, and all the ground pins are put together. Okay, the thing that I have taken into this particular symbol is all the other alternate function also I have summarized here, so that it is easier for us to understand what is the functionality for this particular pin. So let us say if we talk about pin number 44, so that is PA11, and this PA11 has other function like SPI MISO, then event out, then TSG G4I2, then it is having UART T1 CTS, like that. Okay, so it becomes bit easier for the designer to search particular application or particular pin for their applications. Okay, so I have tried putting all the net names that for the purpose that we are going to utilize. If you want to make the symbol little bit easy for your convenient, what you can do is you can remove all the other functionalities and only keep your port names. Okay, so only if you keep port names, that is more than enough. Okay, since this particular device is already having internal oscillators, okay, so we will not be using external oscillator or external crystal for clock generation. We will be trying to use internal oscillator for this particular application. Okay, so very first thing that we try to target is what is the power supply. Okay, so first of all we have to power up the device, so for that we have to design a power supply, and our power supply for this particular design will be 3.3 volt application. Okay, so this particular microcontroller will be powered with 3.3 volt application. For that, what I have done is I have taken an external connector which will be taking a power supply input from some source of 5 volt. So 5 volt regulated power supply is coming from somewhere, and that is going through a fuse, okay, of 375 milliamperes fuse it is. Okay, and I have put one protection device also, that is TVS diode of 5 volt, so that it clamps the any a spike or something to 5 volt. Okay, and this is one of the best linear regulator, that is LDO. Okay, that is there from Texas Instrument, and it has a capability of around 800 milliampere rating. Okay, so this is a SOT package. Okay, and you can see we have 5 volt to 3.3 volt conversion very easily. All right, and these are a 10 microfarad capacitor, ceramic capacitor, 0.1 microfarad capacitor, that is acting as a filter capacitor, and 100 microfarad capacitor I have put as aluminum electrolytic capacitor. If you want, you can change this value to little bit higher rating also, that is, let's say 220 microfarad or so. Okay, now if you do not want to use aluminum electrolytic capacitor, then you have to go ahead with ceramic capacitor of bit higher values, let's say 47 microfarad or something like that, some two numbers or something like that. Okay, so this is how you can have the design. One more option that I have given is I have given one jumper here. Okay, so in this jumper, if you connect this particular device with your USB connector, then USB V bus power will be there, which will be coming from your laptop. Okay, and this 5 volt you can sort this through a jumper, and this jumper will get sorted, and this 5 volt will be appearing at this point. Okay, so you don't have to connect this external power supply, regulated power supply. Okay, now one more thing that you can do is, let's say suppose you are taking this power not a 5 volt, it can be let's say 6 volt or 7 volt or 9 volt, or a power coming from battery or something like that. So in that case, what you can do is you have to have one stage which will be like that connector is coming which is going to give you, let's say a 9 volt, and from there you have to have a LDO which will be converting to 5 volt. Okay, so 5 volt LDO you try to put here. You can utilize LM7805, okay, of TO220 package. So LM7805 or LM340, okay, 340T, okay, LM340T. So these are the two devices that are very popular and very sturdy. So you can convert your power supply input to 5 volt rating, and then this 5 volt rating, after that it will come here, and then it will convert to 3.3 volt. Okay, so this is another way of like having a very general power supply for your board. So this was all about power supply. Now let us talk about decoupling capacitor that is utilized for the all the power supply pins of the microcontroller. So nearby each of the VDD pins, you have to connect one decoupling capacitor. So for that, what I have done is I have connected a 0.1 microfarad, 4 numbers, because 4 VDD pins were there. Okay, and one additional 10 microfarad bulk capacitor will be connected to one of the VDD pin. Okay, so you have to make sure that each of these capacitors should be very close to the respective VDD pin. Okay, VDD pin. Similar to that, for VDD-A supply, I have connected one ferrite bead here. So this ferrite bead of 100 ohm ratings, and this VDD is anyway going to get connected to VDD-A, and this VDD-A will be supplied to your analog supply voltage with a 0.1 microfarad decoupling capacitor and 1 microfarad capacitor. Okay, and LCD supply is also connected with 0.47 microfarad external capacitor. So this is the decoupling capacitor that will be connected to your microcontroller circuits. Okay, so we have completed our VDD, VDDA, VLCD and VSS. All these pins have been completed and the power supply is done. Okay, so you can see our 3.3 volt has been connected, and what I have done, very good thing is, this 3V3 power, okay, has been, let's say, connected to or made change to VDD, so that I can utilize VDD everywhere. So if you want, you can put one like a 0 ohm resistor of, let's say, 1206 package, so that you can change your net name. Or otherwise, if you do not want to change net name through a resistor, you can directly change this particular net name as VDD, so that VDD will be used everywhere. So basically I will be using VDD as 3.3 volt. Okay, and 5 volt will be used, or 5 volt can also be used as VCC in my power supply. So my 3V3 will be used as VDD and 5 volt will be used as VCC or 5 volt. So these two terminologies I will be using in this circuit design interchangeably. Okay. Good. As I was talking about programming and debug, so programming and debug, before that what happens is, let us say I have to have a requirement of SWD programming, like serial wire debug programming. So in that case I have taken SWD CLK programming and like clock generation, and then SWDIO. Okay, so these two pins are required for your serial wire debug. Now two more pins I have utilized. One pin is used for like power supply, another pin is used, pin number 3, which will be used for your ground pin. Okay, then one pin which is pin number 5, that is used for your reset signal. Okay, and other places you will see generally STM microcontroller are coming up with SWO signal. Okay, so this SWO signal will be used at pin number 6. However, in this particular microcontroller there is no SWO signal, so I have anyway connected to PB3. If you want, you can remove this particular resistor so that it doesn't get connected. Okay, and still this particular programming will be very easy. Alright, now to reset this particular microcontroller, anyway there was internal pull-up resistor for this particular microcontroller. However, to be like safer side, I have always connected, or always recommend you to connect external resistor for your application. So once this push button is pressed, then what will happen is this NRST signal will be pulled low, and this is how it will reset the microcontroller when it is powered up. Okay, and you have to make sure that there is a pull-up resistor always, otherwise it will not switch on, the microcontroller will not get switched on at all. So you have to make sure the NRST pin must be pulled up. Okay, now there is boot signal. So bootloader, what I have done is I have put here boot 0. Boot 0 is connected here at this point. Okay, so you can see boot 0 is connected through a 10 kilo ohm pull down resistor, and if you want, you can have a choice of having a pull up resistor also with 680 ohm upward. You can change this value to 1 kilo ohm also, or let's say 470 ohm, based on the requirement that will be needed, but that is not needed right now, so I will not discuss much on that. You can directly use this and it will work. Now let us talk about some of the peripherals that we have connected in this particular microcontroller circuit design. So very first thing that is always utilized is LED connection. Okay, so LED connection, very simple way is this one. Okay, so very simple way, what you have to do is you have to connect one of the MCU pin, and once it goes high, what will happen, this particular LED will start glowing. Okay, D4 LED will start glowing. So you can change the value of resistor based on your requirement of intensity of your LED. If you increase the value of a resistor, the current flowing through this will be less and LED will start glowing little bit dimmer. Okay, dim. And if you reduce the value, let's say 220 ohm or let's say 49 ohm or something like that, in that case what will happen, the LED will start glowing very higher. So you have to make sure the current that is flowing through this particular line must not exceed the maximum capacity of your source capability of microcontroller. So source capability of microcontroller pin is, let's say, 20 milliampere. So you make sure that you do not draw more than 10 milliamps. Okay, otherwise your microcontroller IO pin may fail. Okay, so similar to that, another connection is there, user LED 1, which is connected to another LEDs. Okay, so these two LEDs can be utilized for your different functionalities. Another way of connecting the LEDs are something like this, which what you can do is like 3v3 you can connect like this and put one resistor and then put your LED. Okay, and then you connect here your microcontroller pin as a sync pin. Okay, so this will be acting as sync pin. So you can put a user LED, let's say 4. So user LED 4 will be connected to one of the microcontroller GPIO, and what will happen is whenever this GPIO pin will go low, then it will start glowing, and whenever it will go high, then it will stop glowing. So this is already I have discussed with you various techniques of LED connection. One very powerful technique of connecting your LED is through MOSFET. Okay, so where there is a need of very high current to drive the LED, so that you can have let's say flash LEDs or something like that, or maybe RGB LEDs. So in that case you need to have, you cannot source or sync current through the microcontroller pin. So this source, this microcontroller pin which is connected to LED 0, that is going to be connected to my gate, and this is my drain, this is my source. Okay, so once this goes high, what will happen is this will enable the gate, and this is how the drain source will get sorted, that is it will start working and the LED will start glowing. Okay, so this is another way of connecting the LEDs. So you have seen around 3 kinds of LEDs connection. So you can see various kinds of LEDs. One are like some are like SMDs, some are through hole LEDs, and they are of different colors, or like colorless, or anything that you need. Okay, next connection is push button and dip switches, which are very essential these days. So push buttons, whenever you push the button, what will happen, this is the push button connection, let us say. So it is connected through a resistor, and this is the connection through the microcontroller pin PB, user PB0. Okay, so right now it is seeing high. Okay, so what happens is, as soon as you press this will get connected, and as soon as you press this will pull out to ground, and it will become low. So this MCU pin will become low. It means my push button has been pressed. So as soon as it is pressed, you can take up some actions, like you can glow some LEDs, or maybe you can interrupt some routine or something like that. Similar to that, another push button is also connected in this particular design. Another way of having the changing a port change is like dip switches. So dip switches, what happens, you can see these are the dip switches that you can see. Okay, so you can push up or down. So if you push up, it will get connected. It means like from here right to left, if you push, so it will get connected. Okay, so connected to 3.3. So this user dip switch 0 will see high once you press this side. Okay, or if you keep it this side, this will be always open, so it will be pulled down, that is it is low. So there are possibility of with these two dip switches, you can have 4 possibilities of your these two particular pins of your microcontroller, that can be 0 0 0 1 1 0 1 1. So you have 4 different status to set up this particular microcontroller with these two dip switches. So you have a good understanding of LED connection, push button connection, dip switches connections, and their different kinds of uses. Okay, and all these you can take it from Worth Electronics. Worth Electronics is one of the best manufacturer for LEDs or deep switches or push buttons and various other components are also there, like EMI, MC components, connectors and everything. So this is one of the best company that I have seen. Now let us try to understand how we can connect to ADCs. So to connect to ADCs, let us say we want to measure the or monitor the power supply voltage that is there with us, which is 3V3, that is VDD. Okay, so this 3V3 VDD will be voltage division. So I am doing voltage division with this one so that it becomes almost 3.3 by how many times? This is 20 by 50. Okay, so 2 by 5 times. Okay, so this is how this much voltage will come as at VDD X, and instead of directly sending it to ADC pin, what I am doing is I am passing it through a voltage buffer, so this buffer signal is always recommended. Okay, so this buffer amplifier will give you a strength of the output signal, and this can go to a low pass filter. I have put here low pass filter. Okay, with 15.9 kilohertz or something like that. You can have like 1 by 2 pi RC to calculate your cutoff frequency. Okay, so this R is 100 ohm and C is 0.1 microfarad. So with that you will be finding your cutoff frequency of your low pass filter, and then send it to your ADC input 8. So ADC input 8 will be measuring your VDD power supply voltage level based on the voltage that is coming through this buffer. So this is one of the best technique for that. There is external interface that I was talking to you about. So this is the external interface. Either you can utilize a header kind of thing, or you can utilize a box like a part number. So this two part number I have given it for you for your convenience. Okay, the external board is getting powered by this VDD itself. Okay, so this pin number 1 is powering up and ground is also going, so there is no mismatch or something like that. Then there is an enable signal that is going from our board to that daughter board, the target board. Okay, then there is a on off signal that is coming as a status to my microcontroller. So this microcontroller will receive this particular on off signal, and it will determine whether the board is powered up or not. Okay, there is one parameter that is coming from the target board to measure ADC 0. So ADC 0 is coming here, so I am passing it through the the voltage buffer, and this buffer is again going to one of the ADC of my microcontroller, and this is going to measure the ADC value for that. There is a requirement of PWM to the external board, so this external board is actually receiving one of the PWM signal from my microcontroller to the external board. So this is how ADC and external board can be done. Okay, let us talk about some of the other sensors. Let's say IR sensor. So this is kind of IR receiver which is going to receive something. So what happens is, suppose you press one button to your remote or something, TV remote or let's say Wi-Fi remote or anything. So it will receive and it will generate some output signal. This output signal will go to your microcontroller GPIO, and it will give you an indication that okay, something has been received, and based on that what will happen, you will take up some action. Okay, so this is how, and it is very popular device from Vijay. Okay, so Vijay has produced this particular IR sensor, very user friendly and very sturdy device, TSOP13436. So TSOP13436 IR receiver is very sturdy and very good device, I feel, and I have utilized this particular device in many of my applications for sensor applications. Okay, now let us talk about temperature sensors. So temperature sensors, I have utilized one of the analog temperature sensor which is of the capability of 10 millivolt per degree centigrade. Okay, so this can go as low as -40 degree centigrade to 150 degree centigrade range. Okay, so this can measure up to this much temperature. And what happens is whenever it is connected on the board, and it is generating one output signal based on the temperature that it is seeing. So let us say right now it is 40 degree centigrade. So 40 degree centigrade it may generate up to around like 900 millivolt range, and 900 millivolt will be seen at temperature sensor 1, which is going to my ADC. So ADC will see a value of around the voltage, analog voltage, and based on that you can determine what is the temperature that is there from the temperature sensor characteristic that is given in the data sheet of this particular device. So this particular device has the data sheet temperature sensor characteristics, and that will give you various values of voltage output based on the different temperature sensors, based on the different temperature that it is measuring, right? What you can do is you can replace this particular device with Texas Instrument device also. So instead of having a TC1047A, you can utilize a TMP235A. Okay, so this is also SOT23 package device, and this is also low cost device with same functionality and everything. It also gives you 10 millivolt per degree centigrade accuracy. Okay, so for each degree centigrade change, there will be a change of 10 millivolt voltage ratings. So if you see the characteristics of this particular device, transfer characteristics, as I was telling you, let us say at minus 40 degree centigrade it is giving you 100 millivolt. Okay, let us say your temperature range right now is 40 degree centigrade, right? Like 40 degree centigrade is the environment temperature, then you will be seeing the output voltage of around 900 volt. Okay, so this is what I was telling you. So what happens is, let us say at 45 degree centigrade, what will happen? For each 1 degree rise, there is a rise of 10 millivolt. So in that case, what will happen? 41 degree centigrade, it will become 910 millivolt. Okay. So that's the reason at 45 degree centigrade it is becoming 10 into 5, that is 950 millivolt. Okay, so similar to that you can go as high as up to 150 millivolt, 150 degree centigrade, and for that you will be getting 2000 millivolt, that is 2 volt. So that's the reason I am not using any voltage division or something at the output, because 2 volt is sufficient for my ADC to measure. So it is a good understanding. Sometimes what happens is this particular SOT package is not available abundantly, and like in market you will be seeing SC70 package. So what you can do is, instead of using this particular device, you can also use SC70 package. So this also a device I have utilized, and given in this particular circuit. So it has 5 pins, and instead of that you can see 2 pins are not connected pin, and only 3 pins are used. One is V out pin, which is as usual going to give you 10 millivolt per degree centigrade output. Okay, and one ground and one VDD pin, which is going to be supplied by the supply voltage. Okay. Good. So this is the output of your analog temperature sensors. What you can do is, directly you can send it to your ADC value, or if it is always recommended, instead of using this way, what you can do is, directly this temp signal, output signal, you can connect it to buffer, and after that if you want you can send it to ADC. So this is also one of the recommended method to send it to your ADC values. Or what you can do is, instead of sending it to tempo, temp out 3 can be sent here at the buffer. Okay, so you can put it temp out 3 here at the buffer, and because this is already low pass filter available here. Okay, so after low pass filter you send it to the buffer, and then buffer output signal you can send it to your ADC for the measurement of temperature sensor. Okay, alright, so if you have any questions till now you can ask. Let us move to the next peripherals. There are several temperature sensors that is there available in the market by different manufacturers. So one of the very popular device that I see, and which is very abundantly used in our market, is LM35C. Okay, so LM35 series micro analog temperature sensors are very user friendly, and they have a capability of either 3.3 volt input or 5 volt input, and they will also give you output voltage sufficient, which can be directly connected to your ADC. Okay, so this is the ADC that you can send it to your microcontroller ADC or external ADC to measure the analog voltage, and based on that you can decide what is the temperature of your device. Okay, and this is again one LPF full low pass filter that has been designed here to do that job. So this is all about temperature sensors that we have attached in this particular microcontroller circuit design. Now we'll talk about I2C applications. So let us say a very popular I2C application is connecting EEPROMs. Okay, so EEPROMs, this device is already having EEPROM, like my STM32 microcontroller which we are talking about right now, STM32L053, is having already 2 kilobits of EEPROMs. However, what I have done is I have connected one external EEPROM with 4 kilobits of capability. Okay, So as you can see, it has like address pin of A1, A2. If you want, you can put all both of them as 0. Otherwise, if you have to have like several EEPROMs for different applications, what you can do is you can connect up to 4 like different EEPROMs. So for that, what you have to do, either you have to put A1, A2 as two different like let's say A1 and A2. So 0 0 0 1 1 0 1 1. So these 4 status, if you measure put them, then you will be able to connect 4 different EEPROMs. Okay. Now if you have not pulled up your I2C lines in your microcontroller side, then you have to connect here to like pull up resistor through VDD. Okay, VDD. And the values you can if you have to have little bit higher speed, then keep the values of the resistor lower, and if you have to have lower speed, then keep the values of resistor higher. Okay, so this depends. So I will recommend you that you can keep it 2.2 kilo ohm both. Okay, so which will be of little bit of higher like speed. So this is what the EEPROM interface with your I2C from your microcontroller. As I was mentioning about the buzzers that is used always almost, so buzzers are used for audio application or like like the beep applications. So what you can do is this is a 2.7 kilohertz like buzzer. So in that I will be putting buzzer as like PWM signal. So this will be coming from my microcontroller PWM signal of 2.7 kilohertz with 50% duty cycle. Okay, and this is voltage divided because it just need 0.7 like volt to switch on this particular transistor. So I have just put 1 kilo ohm 1 kilo ohm, so it will be going to give you around 1.65 volt here, so it will easily turn on this particular transistor. If you want, you can replace this particular transistor with a MOSFET. Okay, so MOSFET can be always utilized, which is actually preferred because it doesn't have any like a lot of drop across this. So this will be my drain, this will be my gate, and this will be my source. So the part numbers that you can utilize for this particular buzzer is like let's say BSS 138, okay, PW 115, or otherwise you can utilize 2N7002K. Okay, so these two you can utilize very easily for this particular application. If you want, you can like increase this particular value so that you can increase this value also. Otherwise there is no need. If you are going to use this MOSFET, then in that case the series resistance will be reduced to 100 ohm or 220 ohm max. Okay, so do not increase more than 220 ohms if you are going to use MOSFET for this application. Okay, now this buzzer magnetic transducer buzzer is connected here. This is taken from CUI devices, which is CST32L053. Okay, if you have a 5 volt rating, then you utilize 951. Okay, so the part number will be CST-951AP for 5 volt application, and for 3.3 volt application audio buzzer you can utilize CST-931AP. Okay, 931AP. So 931 will be for 3.3 volt application and 951 will be for 5 volt application. This diode is actually freewheeling diode. So this freewheeling diode is actually recommended by the manufacturer, and otherwise it will not work. So you have to utilize this particular diode in this particular fashion. There are several cases where what you have to do is you have to attach a resistor across the transducers. So in that case I have given a provision for resistor also, which will be not used right now in this particular circuit. So if there is a need of resistor, then you will be removing the diode and putting the resistor. So in this board design I have taken that flexibility as well, so that option is also given to put a resistor across this particular audio buzzer. Now let us talk about NTC, which is generally like used. So NTC temperature sensors are very like user friendly and they are sturdy. So they are generally used in, let's say, oxygen concentrator, or like very big devices, let's say where you need to have like this NTC can be like put on the body of the device, and it can be screwed up, right? So you can put a screw and it will be very sturdy, and these two output lines that can be connected to the connector that I have put here. Okay, so this will generate a resistance based on this based on the temperature that it is going to encounter. Okay. So as you can see at 25 degrees centigrade, the resistance value will be 10 kilo ohm, and as my temperature increases, my resistance value will decrease, and as my temperature decreases, resistance value will increase. So that's the understanding of this particular negative temperature coefficient temperature sensors. Okay. So I have put already a fixed resistor which is going to convert. Let's say this is right now 10 kilo ohm at 25 degrees centigrade. So this my Vx will be 1.65 volt. Why? Because 10 kilo ohm is down I have put. Okay. So this 1.65 volt will be coming through the buffer, and this buffer I have put here, and it is going after a low pass filter to my ADC. So this is my low pass filter and going to the temperature sensor measurement for the ADC. So ADC will like measure the voltage value, and based on that it will decide what is the temperature, because you have already RT values, and you can compare what is the RT, and based on that you can take your corresponding temperature from the table. So this is how it is done. I have given a provision of power I mean amplification also. So if this particular voltage output is very low, then you can amplify based on your convenience. Okay. So this is what about NTC temperature sensor. Now let us talk about ambient light sensor that also I have given in this particular application. So this is my ambient light sensor that is taken from Vijay. Okay. This NTC was also taken from Vijay. So Vijay is, I feel, one of the very good company for sensors, resistor, capacitors, passive devices, active devices, all those things. Okay. So as I was talking about a light sensor, okay, so ambient light sensor, this seems to be like this. So what happens is this is going to measure the ambient light sensor, that is basically it is going to receive that light, and it is going to give you the output voltage based on that particular measurement. Okay, so this will be connected to my ADC, and this ADC will give you the understanding what is the amount of light that is there in your environment. So if the light is low, then what you can do is, based on this decision, you can switch on the lights in your room or in your inside your car or everywhere. Okay, so these are used in your cinema theaters or maybe home appliances, automotives, everywhere. Okay, for your ambient light sensor application. Okay, so coming to the next, we are going to talk about pressure sensors. So pressure sensors is also like one of the best sensors that are actually required these days. So what is the amount of pressure? Generally it is used in blood pressure monitor, BPMs, or maybe like CPAP. Okay, CPAP. Okay, CPAP, or maybe it is also used in let's say syringe pumps, or maybe oxygen concentrators. So a lot of medical applications are there where you need to utilize pressure sensors. So for that, what I have done is I have taken a 5 volt input supply, and this V output is going to the amplifier. So this amplifier is going to amplify the input to 57 times, and this 57 times it is going to one low pass filter and going to the pressure sensor ADC. So this is also going to get connected to my ADC. Okay. So as you have seen a lot of sensors and lot of monitoring voltage that has to be monitored through ADCs. So you can see we have a requirement of several ADCs of my microcontroller. So almost all the ADCs channel will be utilized of your microcontrollers. In that case, what we do is we do not use internal ADC that is there in the microcontroller. Instead of that, we have a choice of using some external ADC also. So what we'll do is, in this session we'll try to understand how we can connect all these outputs to my external ADC as well. Okay. So for that, what I will do is I'll connect a multiplexer switch. So this multiplexer switch can take 8 signals. So it is going to take one signal and then convert it to mux data output. Okay, so what happens is these are the select lines mux A0, A1, A2. So this is going to give you 0, 0, 0, 0, 0, 1, 0, 1, 0. So these 3 lines have been connected to my MCU GPIO, and they will be selected based on the status of the GPIOs. So let us say 0, 0, 0 is the state of all the 3 lines, then S1 signal will be connected, and this ADC1 will be passed to my D signal, that is my mux data, and mux data will be going to the input of your ADC. Okay. So this is how you can route your signals, several signals directly. So instead of using external also, what you can do is you can utilize this particular mux, okay, and you can send your ADC signal to only single channel ADC of your microcontroller also. Okay, so that is one of the best method. So this is how you can like name your signals as per your requirement. Okay. One more thing what you have to do is you have to make sure, like directly you cannot send 3.3 volt and 5 volts. What you have to do is this 3.3 volt you have to send it through a voltage division, and let's say this is my 3V3 ADC. Okay, and this is my 3V3. So this 3V3 will be like voltage divided and then send it here. Similar to that, 5 volt also you have to send it like that. So this is just a way of connecting. I am like showing it to you, but actual way will be little different, the amount of reference voltage what is there. Let's say you have a reference voltage of 2.5 volt. Okay, so the input signal must be lesser than 2.5 volt, that is the for sure. Let's say you have a voltage reference of 3 volt, then input signal must be lower than 3 volt. Okay, so that's the understanding should be there. Okay, now let us talk about external ADC that we can like feed this mux data, and then that can generate my ADC values. So for that, what I have done is I have taken one external ADC which is there from analog devices, which is AD7684. So AD7684 is true differential ADC. However, there is no differential signal, so I have connected my negative signal as ground. Okay, so this is a single-ended ADC. Right now it is working. So in that case, what happens is mux data is coming and I am passing it through a buffer. So this buffer is giving the regenerated signal at the VADC. So V underscore ADC is coming here, and then I am passing it through one low pass filter, and this low pass filter is again changing. If you want, you can change this low pass filter of little bit lower cutoff frequency by increasing the resistance value to 100 ohm to let's say 1 kilo ohm, you can make it. Or even if you want to reduce this, because all the values were DC signal, so you can reduce your low pass filter cutoff. So for that you can go up to around 10 kilo ohm. Okay, so 10 kilo ohm also you can put. So I'll recommend you keep it 100 ohm, so that you don't have to worry about your low pass filter cutoff frequency at all. Then again it is going to pass through a buffer. Otherwise, if you want, you can directly send it to the ADC, but it is always recommended as many times buffer possible you can always send it, and then send it to your VANA to your input of your ADC. And this input of your ADC is going to generate based on the ADC conversion. So this is my you can see 7864 I have taken, which is going to be 16-bit ADC. Okay, 16-bit ADC, and with 100 kilo samples per second. So this D out data will be going to my ADC data of my microcontroller, and ADC this is my SPI actually connectivity. So SPI interface is there. So in that case, what happens is SPI clock is coming as input here, and SPI this is going to the data to the microcontroller. So that will be SPI master in slave out. So this is how it is going to get connected to my SPI MISO to ADC data. And ADC CS can be connected to SPI NSS, that is select lines, so you can use this particular understanding. If you have several other ADC signals or something like that, then you can utilize this. Otherwise you can always put it either high or low based on the requirement that you need. I have utilized one V reference signal for this particular ADC VREF, which is going to be generated by ADR06, and this ADR06 is going to generate a 3 volt signal, and this 3 volt signal is acting as a reference signal. That's the reason I have told you, make sure your mux data that is coming as your analog signal input must be lower than 3 volt. Okay, so you have to make sure whatever the data that you have to, whatever the signal that you have to measure as a ADC value, your analog value must be lower than 3 volt. Okay. That's all. Other this particular device you can select based on your requirement. So I have given you the complete table of ADCs. So different ADCs are there, like 18-bit ADCs are there, 16-bit are there, 14 bits are there. Okay, so you can utilize 14 bits, let's say AD7940 also. Okay, if you have to have a little bit higher speed, then you can go ahead with AD7688 also. So I have utilized several of these ADCs for different applications based on the speed requirement that is there in our applications. Now let us talk about various other applications, like we will talk about USB connections. So I have connected one micro USB, okay, so that is taken from Worth Electronics. You can take it any manufacturer, that is not a problem. However, this V bus signal and D plus D minus signal is there. ID I have left it unconnected. This is sealed, so sealed is also connected to my ground and ground is connected, okay. So this is how it is there. So I have put here one link for ESD connection or application note for ESD protection techniques, okay. So what I have done is I have utilized one of the TVS diode, that is ESD protection diode, which is 824011, okay. So that is also taken from Worth Electronics, and you can see this is actually like this in real. So what is happening is IO2, that is pin number 4, is connected to USB positive, and pin number IO1 is connected to USB negative, that is pin number 3, okay. So pin number 3 is connected to this, and V bus is also protected through this particular unidirectional ESD diode. Alright, so this is one way of protecting your ESD. You can utilize other protection diodes which can be looking something like this also which can be acting as a bidirectional. So this is also one method to connect. So these lines will be connected to your USB P and ground, and similar to that USB N and ground, and this VDD and V bus and ground, okay. So same way you can utilize 3 of these kind of ESD diode for your application. Okay, so now USB P and USB N is going to get connected to my USB to UART bridge. So this is a USB to UART bridge I have utilized from Silicon Lab, and this Silicon Lab USB to UART bridge, what it is doing is it is going to take up the UART signal, okay, to this TXD and RXD lines. Alright, so as you can see, this MCU signal which connected to my UART, so I have utilized 2 UARTs, one was UART 1 and UART 2. So UART 2 is connected to this particular UART RX and UART TX of my microcontroller, and this TXD RXD is connected here. So what is happening is this USB P and USB N is connected to my USB connector device that I was showing you just now, okay. So this is my USB connector, so this is how it is going to be connected, okay. It is very simple IC. You have to just utilize your V bus signal which is coming here, and then you put your VDD with 4.7 microfarad, and this is how it is very easy. You can connect it like this. Another very useful application is RS485 and RS232 communications. So what I have done is UART to RS232 communication, what I have done here is the MCU signal that is coming as UART signal, okay. So this UART signal is coming to TX RS232 and RX RS232, okay. So by mistake here it is renamed as like this. What you have to do is you have to rename according to this one, okay. So that you have to understand, okay. Now this is a Max 3221 EAE plus device. This is there from Maxim integrated, that is a part of analog devices. So I have already written here analog devices. So these are the 2 ICs that you can utilize, Max 3221 CAE or EAE, based on the temperature ratings that you need. Otherwise you can directly replace this particular IC using Renesas ICs, okay. So Renesas IC is also having ICL3221 IAZ or CAZ, okay. Good. So this is very simple design. You have to just utilize one of the ceramic capacitor here at charge capacitor C1 plus and C1 minus, then C2 plus C2 minus, 0.1 microfarad capacitor, okay. So these are 0.1 microfarad 50 volt ceramic capacitor is enough, okay. 0.1 microfarad 50 volt or 25 volt or even 25 volt will do, okay. So 50 volt are more general, so you can utilize 50 volt ratings, okay. Similar to that, these 2 capacitors are also same, okay. That is used as V plus and V minus. Now this is my power supply 3.3 volt. If you want, you can utilize 5 volt power supply as well. This is capable of taking 5 volt power supply, and this will be the output signal towards the RS232 side. So this is my RS232 side, okay, which is going to get connected to my D sub 9 connector, and this is my UART side, that is microcontroller side, okay. and this is the RS-232 transceiver from UART to RS-232. So you can see I have given a part number for this particular D-sub-9 connector also, that is 6180092111821, and this is from Urth Electronics. Very good part number for D-sub-9 connectors, so you can utilize directly. Now why I am going to utilize this particular change, that is TX RS-232 and RX RS-232, I will tell you just now, because I am not directly taking the UART signal here. I will tell you the reason why it is. What I am going to do is I am going to take another application which is RS-485. So RS-485, same way what will happen is this is like one of the best device from analog devices, which is going to be ADM3061. okay, ADM3061. So that I have utilized in various other applications also, and I have also trained you for this particular device in several of my workshops. And as you can see, there is a data out which is going to be our receiver output. Okay, so that is going to get connected to my receiver of UART. Okay, so this will be connected to my receiver of UART signal, my MCU signal, and from UART transmitter signal it will get connected to my data input. So this is my TX signal and this is my RX signal of UART. Okay. So UART TX signal is going to come as data input to the data input, and it is going to get converted to the RS-485 signal, which will be differential signal at the A and B. Okay, so A is non-inverting output and B is inverting output. So when it is acting as transmitter, okay, in that case you have to pull both the receiver enable and driver enable as high. Okay, so it will act as a transmitter. In that case it will be acting as driver output, and it is going to get connected to my D-sub-9 connector like this. Okay. Now let us say this particular receiver transceivers is working as receiver. In that case you have to utilize these two resistors, like pull it down, so you have to remove these two, 1 2, and you have to utilize these two. Okay, so in this case what will happen is this receiver enable and driver enable will be pulled low, and this will start acting as receiver. So in that case A and B will act as receiver input, like A will be non-inverting receiver input, B will be receiver inverting receiver input, and in that case it will be giving you the data output at RX signal. Okay, so this UART RX signal will be taken. Now what I am going to tell you here is instead of using both the UART to RS-485 and UART to RS-232, I have used a switch, and it can be enabled either RS-232 or RS-485. So this is a multiplexer switch, or you can utilize 2:1 SPDT switch. Okay, SPDT switch, like single pole double throw switch. So what happens is whenever my switch select line, so switch select line is pulled low, so if it is 0, then what will happen is D1 is connected to S1A and D2 is connected to S2A. Okay, so in that case what is going to happen is I have connected my UART signal as UART TX and UART RX, which is going to get connected at D1A to S1A, which is transmitter RS-232, and D2 as RX is going to get connected to RX RS-232. Okay, so this is how when the switch select is low, it is acting as RS-232 converter. Okay. Then whenever my switch select goes high, okay, so in that case what will happen, D1 will get connected to S1B and D2 will get connected to S2B. So in that case what will happen, my UART signals will get diverted to my RS-485 TX and RS-485 RX. So in that case for high, like switch select, if you keep high, then in that case what will happen, this will act as RS-485 converter. So UART to RS-485 also and UART to RS-232 also, both are being used together. Understood? So this is how you can utilize this particular SPDT switch, and this particular SPDT switch is kind of a relay replacement instead of utilizing relays, which will be very bigger, and you have to drive the relay with various other different components like MOSFET, diodes and resistors, and you have to utilize some of the like driver signals also. So instead of that, it is very easy to utilize SPDT switches, and this particular switch is very useful, which is going to be TMUX 1136. This is there from Texas Instruments. Okay, Now, since we have talked about almost all the applications, there are a possibilities that you need to like expand your IOs. Like you are running out of your IOs, like you have a microcontroller with 64 pins. So let's say you have around 51 IOs or something like that, and you need, let's say, 10 more IOs, okay, or 10 more GPIOs if you need. Then you can go ahead with IO expanders. So I'll just give you an example of IO expanders, how it is utilized. So one of the IO expander that I have taken it from microchip technology, so that is MCP23017, okay, MCP23017. So this is with I2C interface. So what I have done is this is the power supply that is going to get connected to VDD, and my SCL and SDA lines are actually pulled up with a 2.2 kilo ohm, and my I2C SCL and I2C SDA is coming from your MCU, okay. So this is how they will be driving the signal, okay. So whatever the GPIOs that you have to connect, you can connect directly to GPIO 0, GPIO A, GPA 0 to GPA 7, and GPB 0 to GPB 7, okay. Now sometimes what happens is you have to reset this particular IO expander. So for that I have just put here a switch as well, okay. Or if you want, you can directly connect to your NRST pin, so you don't have to utilize external switch, like extra switch, that will reduce the cost, okay. And the thing is, I have utilized here like this is address line, so A0, A1, A2. So as you can see, I have pulled it up or pulled it low. So you can see A0 is pulled up and A1, A2 are pulled low, so it can be seen like this: A2, A1, A0. So it is pulled up and 0 0. So it is having 0 0 1 as address lines. So what you can do is you can connect as many as 8 like IO expanders, 8 IO expanders with this particular understandings. Like either you keep all the address lines to 0 0 0, then 0 0 1, 0 1 0. So like that you can connect up to 8 IO expanders, okay. So based on your convenience, you can utilize this particular IO expanders with I2C interfacing. Another very powerful interface that I'll tell you for IO expander is using SPI, okay. So there is a functionality of like SPI like SPI interface also. So what I have done is, another IO expander I have taken from same microchip semiconductor, okay, microchip technology. So this is MCP 23S17. So it was 017, now it is S17. So S is for SPI like a communication interface. So same way you have to have a power signal here, and you have reset. So reset, if you want, you can directly connect it to NRST, so that like the microcontroller reset signal itself like resets this, and you can remove this one. Otherwise you can utilize an external separate push buttons for this particular reset application, okay. Now same way for address lines I have utilized same manner, like it is A2, A1, A0, and then 0 0 1. So I have kept the address line as 0 0 1 for this particular application. Now this is my serial output data, and this is serial input data. Then this is my chip select, and this is my clock okay. So SPI clock. So as you can see, SPI clock is connected here, SPI select line or chip select is connected here, then SPI MOSI, that is master out slave in or serial in or target in. So SPI MOSI, that is master out slave in, so serial in is connected to this, and SPI master in slave out is connected to SPI data output. So all these particular GPIO that can be connected either to drive some LEDs, or let's say push button, or let's say dip switches, or let us say like any kind of, like, let's say switches or something like that, or maybe some fault signal. Let's say some fault signal is coming as high or low, or maybe some indication purposes. So there are various applications, or maybe these particular IO expanders are generally utilized for your keypad application, okay, keypad application or LCD application. So keypad, you need lot of like keys. So for that you may need, let's say, 16 IOs. So for that, these 16 IOs can be utilized for your keypads. Or LCD signal, let's say different segments are there to drive them, you need to have an IO expander. So for that these are used. So this is the way various applications of this IO expanders are there, and you can utilize through either I2C interfaces or SPI interfaces. So this is one of the best applications. So alright guys, if you do have any questions or anything, please ask. So we have almost seen all the applications that were there, like in this particular microcontroller. And if you do have any questions or any queries, still further, I will be available on email or on my contact. You can always share your thoughts or put your queries in the comment box as well. I will be uploading this particular workshop in our series as well. Okay, so this particular video will be helping you to design your own particular circuit design. And if you do have any particular specific requirement of your project design, because this is a kind of general circuit design which is not going to give you a complete like a particular application. It is a collection of several different applications. Okay, so if you do have any kind of questions like that, you can put down your questions in the comment box and we shall be able to answer you out as soon as possible. Thank you.